Welcome to this video in the Acids and Bases chapter. Today we're going to cover three smaller topics and pack them into one video. We're going to be covering acid-base indicators and table M, so make sure you have your C-cert handy, neutralization reactions and predicting your products and balancing the equations, and of course the titration calculation. So if you have not already done so, please make sure you have your companion worksheet handy, have your calculator out, and have acquired your coloring utensils. Without any further ado, let's get started. All right, let's open up episode 1 of this video and talk about acid-base indicators. So if you haven't already done so, grab table M and open it up. Throw in a scenario at you guys. Imagine you have a clear and colorless liquid like this one that's here on your lab bench. You are asked, is this an acid, is it a base, or is it water? Now, you could very well dip your finger in that and taste it, and you know if it's bitter, it's a base, and if it is sour, it's an acid, but that's dangerous, so don't try that. The idea is we need to find an alternate solution, and one of those is to use acid-base indicators to determine the approximate pH. An acid-base indicator is a chemical that can tell you the approximate pH of a solution based on the color that it is when it is dropped in there, or based on the color changes that it undergoes if a solution is manipulated. Acid-base indicators are actually quite complex in the way they work. They take advantage of Le Chatelier's principle. This video is not going to get into that. We're going to just get into what the acid-base indicator can tell you based on the color it is. So if you guys look at table M on your C-cert, you will see there is an entire laundry list here of acid-base indicators. And you will notice they all have a different pH range. That is the range at which they are going to change color from, let's say, here's methyl orange, from red to yellow. Let's look a little closer at methyl orange. So methyl orange is the first of our indicators listed on table M here, and we see that its color change range is 3.1 to 4.4, and the color change is red to yellow. Now, what that means is that if you have methyl orange and you drop it into a clear solution that has a pH below 3.1, so it could be anything, 0 to 3.1, that solution is going to turn red. So you cannot tell the difference between whether that would be a solution with a pH of 1, 2, or 3, they would all look the same. Conversely, if you dropped methyl orange into a solution that had a pH above 4.4, that would wind up turning yellow. So whether your solution had a pH of 5, whether it had a pH of 8, whether it had a pH of 14, they would all be the same degree of yellow. Where we can really take advantage of the methyl orange is looking at the color change range, which in this case is 3.1 to 4.4. Now, once your pH of your solution starts to rise above 3.1, it will no longer appear to be red, and it starts to turn orange, which is a blending of the two colors on the color change range. So if you fall in between, let's say in this case 3.1 to 4.4, you will be neither red nor yellow. You will be the combination of the two colors, which if you did well in art class, you will know is orange. So you will have to take advantage of everything you learned in studio art. Let's just hit on one more example to make sure you got it. Let's use bromthiamyl blue, the second indicator on table M here. You will notice that bromthiamyl blue has a pH range that is significantly different than methyl orange. Bromthiamyl blue, otherwise known as BTB, will change color somewhere in the middle of the pH range, which is really useful when telling acids from bases. What this means is that your bromthiamyl blue, if your solution was 6.0 or lower, you would wind up having bromthiamyl blue show a yellow color in solution. Same if it was 7.6 or above, it would then be blue. If bromthiamyl blue turned green, that would mean your solution had a pH that was between the two ranges, namely 6.0 to 7.6. So now that we know a little bit about pH indicators and how they work, let's get back to our scenario where we were trying to figure out whether this solution here was an acid or a base and what its approximate pH was. Let's start off using phenolphthalein. So if I have phenolphthalein and I drop it in an Erlenmeyer flask with our solution and I notice that it's clear, what does that tell me? Well, it tells me that phenolphthalein, when colorless or clear, must have a pH of 8 or lower, because the color change range would give me some pink lemonade, and if it was above 9, it would give me that deep fuchsia. So now I know that it's below 8. If I tested it with bromthiamyl blue, and it looked yellow, that would tell me now that my solution was not only below 8, but was below 6. If I tested with litmus, right, we know litmus is red to blue, 4.5 to 8.3. I tested with litmus, it looks red. That means my solution must be below 4.5. So now we are starting to narrow it down. Let's hit methyl orange. If the methyl orange is indeed red, that means my solution is 3.1 or below. So based on all that work, I can tell now that I must have in this beaker a solution that has a pH of 3.1 or below. So it's a pretty strong acid, and you probably don't want to taste it. All right, now it is your turn. What I want you to do is pause the video now and, using table M, color in what each increment on the pH scale would be if you used Brom Creasel Green as your indicator. So unpause the video when you are ready for the answers. All right, if you did this correctly, you will see that Brom Creasel Green below 3 is yellow, above 6 is blue, and somewhere in the middle with the 4 and 5, you would get a blending of yellow and blue, you would get green. Depending on your experiment, it is always important to choose your indicators wisely. Why it's important to choose your indicators wisely is if you really want to choose something to tell acids from bases, you want to have a pH range that is somewhere in the middle of the scale, leaving acids one color and bases another. If you wanted to tell strong acids from weak acids, you would want to have something in a color change range, I guess, between 3 and 5, so you could tell, like for instance with methyl orange, whether your acid was strong or it was a weaker acid, which would be above the 4.4 range. Same with strong versus weak bases. You probably want something like thymol blue, which has a color change range of 8.0 to 9.6. So always choose your indicators wisely. So episode 2 of this video is all about writing neutralization reactions and predicting the products when you have an acid reacting with a base. All right, moving on to episode 2, we're going to now delve into neutralization reactions and have you guys predicting your products when you have a reaction between an acid and a base. So essentially, a neutralization reaction is a double replacement reaction between an acid and a base. And as we learned earlier in this unit, the products are always a salt and a water. Fundamentally, neutralization can be thought of as your hydrogen ions all canceling out your hydroxide ions and forming water, which is essentially why, as you guys can see here, your reaction is neither acidic nor basic. To give you guys a good idea what's going on the molecular level, we are going to have an animation where we are mixing hydrochloric acid, a strong acid, with sodium hydroxide, which is a strong base. And I want you guys to pay attention specifically to the number of hydrogen ions that are in solution and where they go and what they form as they meet hydroxide. As we are viewing this, one thing that becomes apparent is that each hydrogen ion, which dissociated and ionized from the hydrochloric acid, finds one of the hydroxides that peeled off the sodium ion, and what we wind up forming is just a lot of water. So if you really look at the true products of this neutralization reaction, yeah, it is double replacement. We have formed an aqueous solution of hydrated sodium and chloride ions along with some water, which is here in the liquid state. So you're really making a slurry of salt water, which is not harmful to you like an acid or a base would be. So each one of those hydrogens cancels out the hydroxide, and so your solution is neither acidic or basic. It is neutral. So now let's get into the doing and start to predict your products of an acid and base reaction. And we are going to treat this just like double replacement, which we learned in the reactions unit. So flashback to that. And you guys know that the products of any acid-base reaction are salts and waters. So how we do this is pretty simple. The first thing we're going to do is assign charges to our reactants and products in each compound. So I'm going to go to my periodic table if I don't have it memorized and say, what's the charge of a hydrogen? Well, that's a +1. What's the charge of phosphate? Well, that's polyatomic ion. Got to go to table E, and that is a 3-. Sodium ion, group 1, so it's +1. Hydroxide, table E, that's a -1. So here we go. Now what we're going to do is swap our species. So they are going to the dance. They are currently dancing with their partners here. They don't like who they're dancing with. They're going to go find new partners. So the first thing I am going to make is my salt. And that is going to be composed of my sodium ion with a +1 and my phosphate ion, which is here, with a 3-. Remember, the charges, we have to drag them across the yield sign. The charges will not change, but our subscripts will change because that helps us balance our new equations for charge so we can make electrically neutral compounds. So here I would make a sodium phosphate, and of course it would be aqueous because it's a group 1 ion that is bonded to phosphate that's here. And I know the second product that I make in any neutralization is water. So that is composed of my hydrogen and my hydroxide. We usually make H2O, but I'm going to tell you guys to write your water as H plus and OH minus because it's ultimately going to help you now balance this entire equation for mass. What goes in has to come out. First thing I'm going to see is that my sodium has 3 here. That means I need 3 there. So I'm going to put a 3 on that. That has now changed our hydroxide to be 3. So now I'm going to have to put a 3 on that. By putting our hydroxide as 3 there, what I have done is I have actually balanced my 3 hydrogens that are there. And if I count everything out, I got, let me see, 1 phosphate, 3 sodium, 3 sodium, 3 hydroxide, 3 hydroxide, 3 hydrogen, 3 hydrogen. My equation is balanced. Okay, now it is your turn. Assign your oxidation numbers, balance your new products that you make for charge, and then balance the entire equation for mass. Pause the video now and then unpause when you're ready for the answers. All right, if you guys did it correctly, here's what you should have gotten. So now let's move on to episode 3 of this video, which is really going to talk about the mathematics of the titration. And for everybody playing along at home, a titration is really a technique where a solution of known concentration, which we will refer to as the titrant, is used to determine the concentration of an unknown solution, which is an analyte. Now, usually if your titrant is an acid, your analyte is a base, and if your analyte is an acid, your titrant is a base because the titration is based on a neutralization reaction. And you will continue adding the titrant to the analyte until neutralization occurs. Now, how do you know when neutralization occurs and your hydrogen ions equal your hydroxide ions? Well, you wind up getting a color change of your indicator. This is called the end point. In some titrations, you will have what is called the equivalence point. That is really where your hydrogen ions will equal exactly your hydroxide ions, but that's usually pretty hard to tell without a pH meter. So for us, since we're going to be using an indicator, we are just going to call it our endpoint. Once you reach the endpoint and you've jotted down all your data, you're ready to do the mathematics of the titration, which uses something called the titration equation, which we see here. Affectionately, we are going to call this equation MAVA equals MUBVUB. That's MAVA equals MUBVUB. It's really number of hydrogen ions, MAVA equals MUBVUB times the number of hydroxide. And on the subsequent slide, I'm going to get into what all these variables are, what they mean, and I'm going to show you how to use this equation with a practice problem. Let's dig into MAVA versus MUBVUB. First thing I'm going to tell you is MAVA equals MUBVUB appears on your CSERT, so it is on your reference table. And you will notice that these variables should look pretty familiar to you. The big M is molarity, the V is volume. The subscript A's and B's stand for acid and base. The volume can be any unit. It is unlike the ideal gas law, which can only be in liters. If you have milliliters, great. If you have deciliters, great. The only thing I'll caution you is that the volume unit needs to be the same on the left as it is on the right. MAVA equals MUBUB we said was on the reference table, but what's not on the reference table are the variables that appear on the left and the right, and that is number of H plus and number of OH minus. What that stands for is the number of ionizable hydrogens on your acid. So for instance, if your acid was HCl and you looked at the dissociation equation, it would have one ionizable hydrogen. Conversely, if you had a hydroxide, which is your base, and you had sodium hydroxide, if we looked at its dissociation equation, it would have one ionizable hydroxide. And remembering this is important because, as you guys know, the more ionizable ions you have, the greater the change in concentration is, and it will affect your mathematics. So don't be that guy. So I want to use MAVA equals MUBUB with a sample calculation to ensure you know what you're doing. So let's now decode this question. It says how much 4.56 molar sodium hydroxide. Now we got a lot of information there. First of all, sodium hydroxide, we see hydroxide, that's our Arrhenius base. So this molarity here must be Mb. And now they're saying how much of that, that's Vb. Looks like we're solving for the volume of the base. And this looks like it's VA, 35 milliliters of 0.750 molar HCl, that is MA. So we were given the internal section of MAVI equals MUBUB. Now we have to figure out how many ionizable hydrogens and hydroxides there are on our acid and our base. If we look at HCl, HCl in the presence of water is going to ionize into one hydrogen and one chloride ion. So this number here is going to be a 1. And the same with the sodium hydroxide. It's going to ionize into one sodium and one hydroxide ion. So this number here is a 1 as well. All that's left to do is now substitute in our values and solve the equation. So I have here 1 times the molarity of the acid, which is 0.750 molar, times its volume, which is 35 milliliters, and that is equal to the molarity of the base, which is 4.56 molar, times its volume, which we don't know, so that's Vb, that's what we're solving for, times the molarity of the base, which is 1. So, since that's my variable, I'm going to divide this side by 4.56 molar times 1, and what I do to one side, I do to the other. Molar, and that is a 1 that's there, so the 1s will cancel, and if I do the math correctly, I get this. It's a pretty simple equation for you to do. It is just some algebra, and I want to point out that I am just answering my question to two significant figures because here my number of hydrogens ions have infinite significant figures, so that doesn't factor into my answer. This gives me 3, that gives me 2, and because we're doing multiplication and division, we obviously want to take the fewest number of significant figures. All right, onward to question 2. You guys are on your own for this one, and I'm going to give you a hint. You will notice that the acid, which is here, has more than one ionizable hydrogen, so make sure you reflect that in your number of hydrogen ions when you are dealing with the MAVI equals MUBUB equation. So pause the video now, try and suss out your variables, and calculate this to the correct number of sig figs. Unpause the video when you are ready for the answer. Okay, if you did that correctly, you should get 12 milliliters of sodium hydroxide once again to two significant figures. Due to my rules of sig figs here, we'll see I have 2. And the base was 1 ionizable hydroxide. Your acid, if you looked at the dissociation equation, gave you 2 ionizable hydrogens that were here. So that is where that 2 came from. All right, on to our third question. Let's see if we can do this. Pause the video now and then unpause when you are ready for the answer. Perfecto. If you did this correctly, we should get 4.49 milliliters of calcium hydroxide, and our answer should be to 3 sig figs in this one. We threw in an extra decimal point here on the H3PO4, and we assumed that this completely dissociates into 3 hydrogen ions, so we had to have a value of 3 here. Our hydroxide this time dissociated into 2 hydroxides, so that's where that 2 came from. And pretty much this is just some simple algebra. Once again, if you have any burning questions on any of the 3 segments that we did in today's video, make sure you bring them to the burning questions segment tomorrow. It has once again been a pleasure to help you through the myriad of chemistry problems that we have in this acid-base unit, and I will most certainly see you on the flip side. Peace out!
That's all, folks.